Right triangle. Hopefully it's clear in this problem what we are trying to maximize or minimize, because in this case of this problem, it does say what we are trying to maximize or minimize. So we will go ahead and write that down, that we are trying to maximize volume. And again, most of what I'm going to be setting up and looking at is not really the calculus part of the problem. Most of what I'm going to be setting up is some of the algebra and rewriting the equations and working with all that. I'll point out here as well that if you need a formula like surface area volume formula, most of the time they're going to give it to you. They are not going to expect you to have like volume of a cone memorized. They'll give you volume of a cone if it's necessary in the problem. So first of all, let's pick out that volume of a cone formula that we use. So we have a right triangle, and its hypotenuse is square root of 3. And what we are doing is we are taking that triangle and spinning it around. Spinning it around, and that will create our cone. So that right triangle spun around creates our cone. And we want to know, because this isn't the only triangle I can build with the hypotenuse of square root of 3, what should my other measurements be in order for the volume to be the biggest? So here's my radius and here's my height of the cone. And volume is 1/3 pi r squared h for volume of cone. So that's the main equation. That's our main equation. And now we need to think about our second equation that is going to put this in terms of one variable. And the other piece of information that we have is that the hypotenuse is square root of 3. So we need a way to relate the radius and the height with that hypotenuse. It's Pythagorean theorem time. All right, because it's a right triangle. And so that will give me another equation that has measurements in terms of r and in terms of h. Square root of 3 squared is 3. And I want to use the thing that will let me substitute in the easiest. And the thing that will let me substitute in the easiest is just subtracting h squared and saying, here's what r squared is. Now, if it'll help you to take the square root and then square it again, then that's fine. But here's r squared, so I can take that and put it in for r squared. That's what I'm going to be doing. So volume is 1/3 pi times r squared times h. And we just decided that r squared is 3 minus h squared. Again, if you want to solve for r being the square root and then square it back out to get the 3 minus h squared, then go ahead and do that. So now we have that volume equation with one variable in it. We have the volume equation with one variable in it. So now we can take the derivative. And let's make it a bit easier to take the derivative because right now it's a product rule. So I'm going to go ahead and distribute out this h. 3 times h here. And then we have h squared times h is h cubed. And now it's a lot easier to take our derivative. Derivative of 3h is 3. Derivative of h cubed is 3h squared. Let's go ahead and distribute out that 1/3 because it'll cancel the 3's. And we want to know when that's 0. Well, it's going to be -1 and +1. Do we want -1 and +1? Nope. We don't want -1 because we don't want our negative height. So that's our height. That makes the radius, if the height is 1, the radius is going to be square root of 2. And you can solve for that in this part of the formula, which will make the volume 1/3 pi times our radius squared times our height. Our height we decided was 1. Our radius we decided was square root of 2. So that will give me square root of 2 squared is 2 times 1. So we have 2 pi over 3. Oh, meters cubed. That's our volume. And that's what would create my maximum. So again, remember, we're going to have our main equation that I'll end up trying to maximize or minimize. In other words, that I'll end up taking the derivative, setting it equal to 0 and all that. That's my main equation. And then I have my secondary equation that will let me put it all in terms of one variable. That's usually the flow of how these problems go. We need some way to write it all in terms of x, or all in terms of h, or all in terms of r. That's the way the flow of these problems usually go. And exactly how they flow and exactly what equations to use depends on the context of the problem. Are we talking about distances? Are we talking about coordinates on an axis? Do we have that kind of equation? Do we have like area, surface area, and volume? Do we have those kind of formulas? It'll just depend. Okay. So now, we're going to look at one more. And this one we won't solve down all the way. This one we won't solve down all the way. The state wants to build a new stretch of highway. And we have some details there about how the highway is going to get built. If this is what the costs are, where should we build? So if we're looking at where we build given what the costs are, we want to look at cost. And what are we looking to do with cost? We're looking to minimize it, right? We're looking to make it as small as possible. We're looking to minimize our cost. Here's the idea. Here's the idea. Is that one proposition we can make to minimize our cost is to just, build the least amount of road necessary. Just connect them in a straight line. Here's the problem. On this upper half of the section on the marsh, it is more money. And connecting it in this straight line will make me have to build in this more expensive area more often. So we could say, well, another proposition would be, okay, well, let's build straight down on this area. That way we are putting in the least amount of road on the marsh possible, and then just connect to the interchange that way. That's not good either, because that needs more road, and more road is going to cost more money. So the idea is that we are looking to have a system that will make it the most efficient possible, that has the best balance of the amount that it costs to add an extra road and the amount that it costs to build on that different area. So we need an equation for cost. If that's what we're looking to minimize, then we need an equation for cost. I'm going to put it as C of x. So we need a cost equation. Well, our cost is $10 million per mile on the marsh. So $10 million per mile on the marsh plus $7 million per mile on dry land. So we will need, what we're going to end up with here is we have x, which is how far away from the bridge I am stopping. That distance from the west end, how far from that west end am I stopping? So as the example that's in the drawing, here's the marsh distance, and here is the dry distance. So we want to think about how we are going to put those two distances. I'll give you a moment to ponder here. How we're going to write those two distances that I just drew in terms of x. Because remember, our goal is to have it all in one variable. So see if you can pick out how we can write both of these in terms of x. And what we'll eventually end up with here is one big ugly equation, but everything's in terms of x. And so from that point, we'd be able to take the derivative, set it equal to 0, and put it in our calculator and go from there. Because remember, you would get a calculator on these questions. There's a hint if you're still stuck. And I want this distance. So in both cases, it's a hypotenuse of a right triangle. So if it's a hypotenuse of a right triangle, then what we should be able to set up is Pythagorean Theorem to get this distance in terms of x. So this squared should be 5 squared plus x squared. And then to solve for it, I would take the square root. So the marsh distance is the square root of 25 plus x squared. And by the same token, the dry land distance, well, it would be the square root of 8 minus x quantity squared plus 3 squared. And to rewrite that, don't forget that this is not 64 minus x squared, because it would expand out. It would be 8 minus x times 8 minus x. So it should be 8 squared is 64. Then we would have a minus 8x and a minus 8x giving me a minus 16x. And then negative x times negative x is positive x squared. Plus 3 squared is 9. So for combining my like terms, that's going to give me 64 and 9, 73, minus 16x plus x squared. So my entire cost equation, my big long cost equation is 10 times the marsh plus 7 times the dry land. So we're going to stick all those in. And now at this point, instead of spending 10 more minutes taking derivatives by hand and working with the calculator, I'm going to pause it there and say that at this point, you would take the derivative and set it equal to 0. Now, if you do want to try taking those derivatives by hand, there's one important bit of doing these derivatives that you want to make sure to be careful of. You want to take a guess? What are these derivatives going to involve? The chain rule is going to happen. So careful of chain rule when you go to take the derivative, set it equal to 0, etc.